afternoon, good evening. It's my pleasure to welcome you to today's ESDS webinar on artificial intelligence in thoracic surgery. The topic is very timely and covers a real broad spectrum of potential applications and topics. And I'm very happy that today we have three excellent speakers to cover some important areas on machine learning and artificial intelligence for us in thoracic surgery. So I'm very happy to welcome Anna Minasyan as the first speaker. She's from Coruna and she's a thoracic surgeon, well versed in application and use of artificial intelligence and machine learning. And she will give us an overview of what the topic is about and what areas are important for thoracic surgeons. As the second speaker, we have Luca Bertolaccini from Milan, from the Institute of Oncology, and as you're aware of, is associate editor for the European Journal of Cardiothoracic Surgery and also on the editorial board of JTCVS. And he will talk about current standards of generative AI and what's important to consider in research topics. And as the third speaker, I'm very happy to welcome Gijs Luijten. He's not a thoracic surgeon, but he actually holds a master in technical medicine. He works at the Institute of Artificial Intelligence in Essen in Germany, and he will talk about 3D instrument collection and what AI can do with hospital data generated from more or less the routine hospital administration system, and will offer some very interesting insights on that topic. So thanks again, Anna, for joining in, and we're looking forward to your presentation.
Okay, thank you. Just 1 second, I will share my screen with all of you. Okay, hello everyone, and thank you for the invitation to participate in this webinar. I will talk about the overview of machine learning and artificial intelligence in thoracic surgery. But before we begin, I would like you all to take a moment and answer this question for yourself. Is artificial intelligence a good term or a confusing one? So what is an AI? The current AI models basically are statistical pattern recognizer. These models, they do not think or understand as a human being would think and understand. So they basically mimic human intelligence. And most importantly, these models, they do not have self-awareness. They are not self-aware entities. Because of the hype and the confusion around this terminology, it is important to speak about a narrow AI and a general AI. Narrow AI, or weak artificial intelligence, it's basically the one that we have nowadays. It focuses on specific tasks, for example, CT scans in healthcare and the algorithm analyzing those CT scans, or for example, self-driving cars. And the general artificial intelligence is something that remains theoretical, hypothetical. It's an artificial intelligence that possesses human-like intelligence. It is also important to mention that artificial intelligence is not here to replace the doctors. It's basically a tool like a mobile phone that helps us in our daily work. So what AI can do for thoracic surgeons? This is the important question. Basically, artificial intelligence can help us in every step of our workflow, starting from preoperative planning, assisting us in diagnosis and enhancing the surgical readiness, intraoperative management of patients, for example, in a surgery, during the robotic surgery, and also post-operatively, it can predict the complications and aid us in patient recovery. As with every other tool that we use in surgery or in medicine in general, we need to know the basics of artificial intelligence too, to be able to apply it in our work. So let's go about and talk a little bit about machine learning and deep learning in a basic level. So the definition of machine learning. Basically, machine learning is a subset of artificial intelligence that provides the systems the ability to understand and automatically learn from data and then give us a model for prediction without being explicitly programmed. This is the important part. And the deep learning is, let's say, a sophisticated class of machine learning. There are basically three types of machine learning applied to medicine: the supervised learning, unsupervised learning, and reinforcement learning. So let's go over these three types of learning. So supervised learning generally involves training the algorithms in previously labeled data sets, where the model learns to predict the outcomes based on input and output pairs. This is very useful, for example, in classification. For example, in our case, classifying a lung nodule if it's a benign or a malignant one. Here we can see some algorithms that are mainly used in supervised learning. And I want you to think about the algorithm as a step-by-step instruction, structured sequence or a cooking recipe that has some ingredients like mathematical equations and then adding some loops, conditions to achieve a specific task, a specific goal. All these algorithms are used to create different type of models for a different type of tasks. For example, we can use these support vector machines, in this case that they did in radiomic analysis of pulmonary nodules in low-dose CT scan for lung cancer detection. Or we can use another algorithm, the random forest, that they did in this case to develop and validate a machine learning risk algorithm for major clinical complications and death after surgery. Or another algorithm like the gradient boosting, and to see if peri-operatively the patient in thoracic surgery, how we could predict the personalized use of red blood cell transfusions, for example. There is an interesting example also from Toronto General Hospital that they used some of these algorithms to train a model called Insight X to assess ex vivo lung perfusion and predict transplant suitability and post-transplant outcomes. Unsupervised learning. As I mentioned before, the supervised learning uses datasets that are previously labeled. And this labeling task is time-consuming and very costly. So here, unsupervised learning can come very handy because it uses datasets that are not labeled. And this technique is very useful for pattern discovery to uncover hidden subtypes of diseases, leading to personalized treatment approaches and improved patient outcomes. And here we can see some of the main algorithms used in this type of learning. The third type of learning is the reinforcement learning. This is basically where the algorithm learn to make a decision based on a trial and error. This is very useful approach and very promising approach in robotic surgery, for example, in aiding intraoperatively in real-time AI assistance. You can think about reinforcement learning as a trainee who starts to learn a surgical procedure, and each time the trainee gets a step done in a correct way, it gets a reward. and each time the trainee makes a mistake, it gets a punishment. Here are some types of the algorithms that are used in reinforcement training. And the deep learning, as I mentioned before, is a more sophisticated, more advanced type of machine learning that utilizes multi-layer neural networks, artificial neural networks, for data representation. This type of learning is very useful in medicine, in image recognition, in image analysis. Probably a lot of you heard or read about convolutional neural networks or transformers. For example, in the heart of ChatGPT lies that algorithm. Some of the examples of deep learning that is used, one of them, a very interesting one, is this one called Sibyl, that was developed in Massachusetts Technological University. This model predicts lung cancer risk by analyzing low-dose CT scans, providing forecasts on potential future cancer development. So the interesting part of this model is this is open source model. So if you have a GitHub profile, you just can go there, search for it, and apply to your patients to analyze the risk that they have. You need to also understand that these learning methods, you do not necessarily use them separately. You can mix and match. For example, you can mix deep learning with supervised learning, unsupervised learning. Like, for example, they did it in this pathology and genomics analysis, where they used machine learning for pathological images to predict 1 year progression-free survival in immunotherapy patient with small cell lung cancer. With all this in mind, as you can see, the AI models, they need a lot of patient data, obviously sensitive data. And the logical question is how we're going to keep the patient privacy and AI. That's why there are some techniques like federated learning systems, where you basically train the models in a different nodes separately, and then you contribute to the global model. So in this way, you do not share your raw data with others, but this is out of the scope of today's presentation. And as a conclusion and future perspective, so basically AI has a big potential and a big role in thoracic surgery and in surgery in general, starting from preoperative planning, from data evaluation, image analysis, and then outcome forecasting and achieving tailored strategies for each patient. And in my opinion, the future trends lie in seamless AI integration in our daily basis, in a greater robotic autonomy, personalized and precise surgery. Also, AI could help in training and simulation, and research and evolution is very important in this case, because as more thoracic surgery data, quality data is included and shared, our models will become better, and they will be better in the learning and in predicting the truly influential factors. With all of this said, it is very important to have in mind that the expertise of a human being is important and crucial in evaluating the AI suggestions and making the surgical decisions. And thank you. Here is my email address for further questions, if you have any. Now I will stop sharing my screen.
Yeah, thank you, Anna, for this really comprehensive overview on the basics of machine learning and artificial intelligence. And particular thank you for being willing to give this presentation just before hopping on a plane. So for the audience, as always, if there are any questions, please use the chat or a Q&A tool, and we will discuss them after the presentations. So the next one on stage I would like to invite is Luca Bertolaccini, and he will present us on standards for the European Journal of Cardiothoracic Surgery, and what can and what cannot be done, and or should and should not be done with generative AI. Luca, looking forward to your presentation.
Okay, thank you so much, Clemens, and I want to thank the Society for the privilege to be here in these beautiful webinars. Okay, the first question to answer is, are we afraid of artificial intelligence? The answers should be no. We should we're afraid of natural stupidity. Because what is not artificial intelligence?
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
AI is not HAL 9000, the supercomputer that grow inside the space station in the beautiful movie of Stanley Kubrick, 2001 Space Odyssey. But AI is a science and an engineering of making intelligent machine, especially intelligent computers program. And this is the first definition of AI in the 1955 from one of the father of the AI, John McCarthy, in his book Basic Question. But artificial intelligence and real life go deeper and deeper in the last year. As you can know and remember, Deep Blue defeated Garry Kasparov at chess. Proved, it's a computer, unsolved the Robbins conjecture, NHAA, driving autonomously from Pittsburgh to San Diego. AI logistic was used to scheduling in 1991 Gulf War the vehicles, cargo, and people. NASA used onboard autonomous and planning program controlled the scheduling of operations for spacecraft. And last but not least, Proverb solve crossword puzzle better than most humans. I think that everyone uses ChatGPT or another generative AI tool. ChatGPT is a large language model, so it's a model that uses a conventional way. GPT stands for Generative Pre-trained Transformer. It is one of the possible generative AI developed by OpenAI. It's a large language model trained to text predictors. The response were based on probable language, and there are factual information that may contain an accuracy that sounds plausible but incorrect. For instance, a large model could invent quote, reference, coding library for R, and LLM access to data were trained, so LLM no access to current information and cannot interpret the language. We have some ethical issue to keep in mind. Luckily, we live and work inside the European Union umbrella. Last year was published the EU Artificial Intelligence Act about the safety and the compliance with fundamental rights. And EU put some limits on the use of biometrical identification. But we have some problem about privacy and data, because generative AI built on information scraped from internet without permission, so there is a violation of the intellectual properties and could collect sensitive information. The cognitive bias is important because the prediction could repeat the cognitive bias found in information. But we have some problem relating to the environment. The training of a LLM produce significant carbon emission, more or less 552 tons of CO2, so more or less more than 100 petrol cars driven for 1 year. And last but not least, there is an invisible human labor to build and cleanse the large LLM. But the growing excitement over ChatGPT potential in medical writing raises two central questions. The first is, how credible is the information generated by ChatGPT? And the second one is, does scientific writing by ChatGPT meet medical journal publication requirement in terms of quality, ethics, integrity? Well, in this beautiful review from Nature Medicine, we could find a summary of the 6 published randomized controlled trials of AI in surgery, where AI was one of the arm of the randomized controlled trial. But AI-generated text may have a role in evidence-based medicine. For instance, the evidence retrieval, the evidence synthesis, the clinical reasoning, the evidence dissemination. But we have some concerns about this. So, although AI can help the researchers to streamline tasks, the human element of creativity, critical thinking, ethical reasoning have never been more important. On the other hand, spending less time to format, to fighting statistical syntax, to refine our biosketches, permit us to focus more on thinking deeply about the research, the results, and the patient care. But pay attention, because AI can introduce the hyposkilia in academic writing, or using AI to search for background material may deter researchers from conducting research. And this is a real key problem. Moreover, relying only on AI can impede language growth. So try these 3 scenarios. The first one, the authors have no concept and demands AI write a manuscript. The scenario number 2, authors know what should be written in the introduction, method, results, and discussion section, input this information, and demands AI to generate a manuscript. The scenario number 3 is the authors write independently. After completion, AI was used as a linguistic checker. Regarding the scenario 1, fortunately, only few authors is likely to attempt. Regarding to scenario 2 and 3, a skillful authors with the input of good data and human touch, the AI could generate a manuscript that is hardly distinguishable from human written. But beware, because detectors and possibly humans can distinguish a manuscript generated by these different 3 scenarios. Okay, but we are already living in a world where the border between the human and the computer-generated content is difficult to draw as never before. So the question is not whether to accept AI or not, but how to manage AI, so not aware of AI. So we need a range of regulatory measures about AI in medical writing. And we have this, we have the recommendation of the World Association of Medical Editors that say that chatbots cannot be an authors. Chatbot cannot meet the requirements for authorship according to the International Committee of Medical Journal Editors. Authors should be transparent when chatbots are used, because the editor find if these chatbots were used. So authors should provide full technical specification and how they were used. On the other hand, authors are responsible for the work performed by chatbots in their paper, and still editors need appropriate tools to detect content generated or altered by AI. manipulated plagiarized text and images, and the paper mill generated documents. So there is a declaration of generative AI in scientific writing, and it's a common declaration from Elsevier to the Annals of Thoracic Surgery, to all the Journal of Thoracic and Cardiovascular Surgery, to the European Journal of Cardiothoracic Surgery, that say that avoid AI tools to analyze data, avoid AI tools to draw insight from data, but AI could be used as basic tool for checking grammar and spelling, and it's really, really an interesting tool for a reference manager. Well, we will discuss in the next ESTS meeting in Budapest in May about the everyday use of a modern AI-powered database. We have in mind to transform the ESTS database in this one. And we should have in mind this, the Kurzweil theory. So, ever-decreasing intervals between the major technological breakthrough in human history is decreasing. So AI will achieve human-level intelligence by 2029. This is the Kurzweil theory. We have a singularity concept on the other end, because at some point, the computers will surpass the human intelligence, and intelligent computer will design even more advanced system, creating a feedback loop of self-improving AI. So, as written in this beautiful scientific fiction book, The Answers from Frederick Brown, a supercomputer is asked if God exists. Its reply, now it does. In conclusion, AI should augment expertise, not replace the human expertise. So we need to balancing the technological innovation with the human skill. And the fundamental distinction between human and AI-dependent writing lies in output and process. Personally, I really love writing papers. I love in the deeply of my heart to write and to make science. So why not cherish a writing time when you could be Jane Austen or Cesare Pavese? It's my preferred Italian writer. So, seasoned, not at all, doctors should encourage the younger generation to write paper not because of fear of being detected, but because of joy of writing. And this will nurture one writing and knowledge, and finally, one overall human power. So, thank you so much. And I could speak about artificial intelligence because my feet are here in my little place, deep in my heart in Italy. Thank you so much.
Yeah, thank you, Luca, for this overview and the excellent summary. So the third presentation now will focus on not thoracic specific, not details not specific to thoracic surgery only, but where AI from other parts of surgery and data administration could be transferred to our field as well, and we're very much looking forward to this, to hearing these aspects.
Thank you very much for the nice introduction, and thank you all for hosting me today. It will be hard to follow up these great speakers before me. I want to talk about a 3D surgical instrument collection for computer vision and extended reality, and about data integration from the hospital into machine learning. I'm a PhD candidate and employed at the Institute for Artificial Intelligence in Medicine, also known as ICIM, where I co-manage the extended reality lab. And we have optical tracking devices to track the body. We have 3D scanners and 3D printers to print what we have scanned. We have surgical navigation equipment, robots, phantoms, and the 3D glasses, the 3D smart glasses, which I enjoy thoroughly to make applications together with my students, for example, for educational purposes. My supervisor is Professor Dr. Jan Aigner, and he leads the artificial intelligence guided therapy groups here at the IKIN. And as I said, today I will start to talk about instruments, a little bit about the motivation, how we made this together with the University of Graz and the University of Aachen, about synthetic scenes and how we can use these in AI. And in the end, well, the interface between research and clinical care, and that is our clinical data. So let's start with the motivation for a 3D surgical data set. There are many common instruments used in general surgery and many medical fields. And then there are more specific instruments. And Rodriguez et al. Identified 40 data sets online, publicly available, to help with machine learning tasks such as annotation, detection, classification, or localization and tracking. The downside of these data sets, as you see here, is they are 2D images or they are videos also in 2D. So the third dimension is lacking. Yet this can still be interesting, for example, to track the instrument and classify it and provide automated documentation of the surgery, thereby relieving a very annoying task. Now, why 3D instruments, besides that it's lacking? In research, especially computer vision research, we see that 3D objects, like in the ShapeNet database, where there are multiple thousands of 3D shapes, can lead to a huge boost in research regarding generative AI, as we've seen before, but then with models or with estimations and also augmented reality applications. And therefore, we wanted to introduce this medical data set as well. So the Clinic of Aachen was kind enough to lend us over 100 of their instruments. Some were specialized for maximal facial surgery, as you see here, and many were also used in general surgery. And we wanted to 3D scan these, which are structured light scanners. These structured light scanners, they use regular light patterns, no radiation, and they project a pattern onto the object. And then another camera films the deformation of this pattern by the shape of the object. Then simultaneously, we also acquire images, and thereby we can make a 3D model as we see here. Now, as you see, these 3D scanners have a tough time with fine structures and also with shiny objects, because the reflection can distort the projected pattern. So we took these 100 instruments and divided them over our 2 scanners. The Artec Leo is generally for larger objects, where AutoScan Inspect is for smaller objects. And we attempted with the AutoScan Inspect, and if that didn't work because the object was too large, we went for the Artec Leo. Now, as said, our instruments are very shiny, and some have very fine details, which might be hard to capture. Therefore, we have 3D scanning spray, which we can apply to the instruments and then acquire a nice scan. After post-processing in multiple ways, we get multiple 3D files resulting from a singular scan. And because the scans are now white, we use Blender, a 3D modeling software, to give these 3D files a realistic color, as you'll see later. And finally, we use Python to make a multitude of these instruments. So from a single instrument, we made more than 1,000 likewise instruments to increase the input for AIs and to enable other researchers. So the entire data set is also open source. The approach is fairly simple. We 3D scan our object in 2 positions, the up and down position, and then we combine them by marking what belongs to what. And after it's merged and the background is removed, we get our 3D instrument, which we then fuse together. And after applying the images recorded, we get our white instrument. We can get a rough error estimation, which is fairly accurate since this is in millimeters and we have less than 0.0 millimeter error in fusing this instrument. And then here you can see how in Blender you can give it a really nice metallic look, but you could also give it a golden look or whatever you desire. Now for the AutoScan Inspect, the process is fairly similar. Again, we scan 2 sides. We remove the background, we fuse the model, and we give it a nice texture, with the notion that this is a robotic arm and is therefore more consistent and slightly more reliable and accurate. So we have over 27 different classes and multiple instruments per class. And we can use this, for example, in an augmented reality setting, where a student at home with the 3D glasses, but also with his phone, can inspect all the instruments, take all the instruments, and before he or she goes to the surgery, already knows the names and the different looks, etc. What did we use these instruments for? We used them to create synthetic scenes. Here you see an example of a synthetic scene where the instruments are clearly used, and these humans are fake humans. These are so-called meta-humans, wherefore we use Unreal meta-humans. Unreal is a game engine used to make games, and we use it to make surgeries. The nice thing about synthetic data is that I can have a perfect ground truth. The ground truth is the so-called input-output pair by my previous speaker. And here we can have a perfect semantic segmentation. So we know what's the instrument, what's the hand. We can also generate depth images, so we know the position of the instrument. And we can train various algorithms using this perfect ground truth for a supervised learning method, prior to going to the patient or prior to requesting the IRB for approval to actually do this with patients. So a use case would be to automatically detect and segment this instrument, as we did with the 2D instruments, but now from a single camera perspective and hopefully in a 3D way. If we think a bit more futuristic, what could we do with this information and with these techniques in the future? We could remove the instrument. Think like when you use an IKEA application to remove your couch and look how a new couch looks. But in this case, we want to remove the instrument or the hand so we can see a bleeding occur behind it, which we would normally not see because it's obstructed. Or we can improve our ergonomical position because we don't have to be bent over the patient to see certain things that otherwise would be covered. Since this is a single perspective, it's very arguable how accurate it would be. But from our futuristic perspective, the OR of the future has multiple cameras being able to leverage this in a nice way. Another use case would be, as you see here, we have a single hand that we recorded. But we can use artificial intelligence, or better said, machine learning, to create various hand grips. This is from GrabNet, another research site that creates realistically or seemingly realistic hand grips on instruments, or in this case, normal objects. And we used it to create grips around our instruments, which are seemingly plausible, although I would be honest, it could improve a lot in plausibility. Yet this is a very fast way to add new instruments and hand grips to our data set, which was also used for a challenge and also available online. Another thing, as I said before, could we use it for surgical navigation? In this case, pose estimation. So the estimation of the location and the orientation. As you can see here, it's not accurate, but now we can start to train different models or fine-tune our model, or try to use different functions, different algorithms that our colleague before showed. And if we do so, we can already detect what model would be more optimal. And therefore, when we go to real-life data, have a better grasp of what would work or what would not work. And again, we have the perfect ground truth, but we could also add noise to this data. So make the data imperfect and use that to improve it. Now, there are many more applications available with 3D objects or 3D instruments and synthetic data. But for the sake of time, I'd like to talk about the interface between research and clinical care. Or mainly, how can we combine our clinical data and make it available for research? I want to note that herefore we have two groups working on it in our institute, and the credit goes to them. We have our Kite group led by Professor Jens Klesik, who allow us to train on the data and leverage our models at the point of care setting. And then we have the SHIP AI group led by Professor Felix Nensa, who make sure that the data from different sources is available in a standardized way, meaning that we can access it with our programs in a unified way. So what I mean is we have 32 clinics and we have over 370 patients, meaning that our data is not heterogeneous. Our data comes from different sources, different formats, yet we still rank as a number 60 worldwide, according to this statistic, which we are very proud of. So how do we do that? First, we look at AI. This is the thing we saw today. And the researcher is this tiny boat. But actually, without the support, it would not be possible. So first, we start with our multimodal data. We have data from our PEG system, from our images system, or from our histopathology system. And we actually have 500 different data systems. And that would be a help to access or use together. So we need to standardize the data and make it in a way that we can access it all together. This is what SHIP does, the Smart Hospital Integration Platform. And then we need a modern IT infrastructure, which is better known as the NVIDIA GPUs, that must be hosted on premise for security and privacy reasons to leverage this standardized data. For this, we use FHIR, Fast Healthcare Interoperable Researches. And I advise everybody to look at this in their own time. But what it does, it makes the data that before was heterogeneous in a unified way. And for all our 500 different data sources, we need to find a way to automate this and that we can access this data. And then we have so-called event listeners, meaning that if I upload a new CT scan, then the event listener will see, hey, there is a new CT scan uploaded, and it makes the CT scan available via a FHIR format, meaning that I can use a query, a program to then access this data and leverages this in one big data list. See it as a huge Excel sheet. So doing this for all our data by now, because this was in April 2024, we probably have over 2 million data points. And the most things are actually service requests, but we have a lot of media files and imaging data and observations from our doctors. And the nice thing is if we have this all in FHIR, that means we have one big sheet where we can find all the data and then a unified way to query this data. Meaning if I want to build a cohort, don't look at this distracting code, but I want to make a cohort. So I want to, for example, know which patients got a PCR confirming their corona in the year 2021. But we also want them to have a radiology exam within 40 days before the or after the test. So we can see if this imaging data actually tells us something about the corona. Now, this is a YAML file. It's basically an advanced text file, which allows us to input that we want them to have this confirmed test and that we want them to have imaging data available. And in this way, we can query to the system and make a cohort in a matter of hours instead of months of manual labor. Then as a researcher, I cannot get access to all this data at once because that would break a lot of privacy laws. And again, in FHIR, if you find a unified way to de-identify the data, then I can get this data in an anonymized way. And I must make the note here that we are part of the hospital. We are an hospital institute, and we are all hospital personnel, which allows us to access this data for our research as long as it's in an anonymized way. And now we can set up several studies with a specified patient cohort, which would otherwise not be possible or take months of labor. But we can also make patient dashboards because we can combine the data from our different sources and have patient-specific dashboards with information that we think is important for this case. Or we can make dashboards for ward-specific. So we want certain information for this ward. This is what SHIP AI gives us. Now, if I want to train on this data, we need to have a place where from the data set or the data in our hospital, we can train it. And ideally, the same GPU can leverage this to our clinicians. And the clinicians can actually give us feedback on how good it is. For this, we have a huge GPU cluster, which was funded through several grants. And it's hosted on-premise and maintained by us, which allows us to have this integration, which is crucial. Now, let me show some quick examples, which we actually already have in the clinics. Our clinicians can use it to automate segmentations. They can check it themselves, give us feedback, and use it for various cases. Or they can interact with the data. It's in German, but they can click a certain segmented spot and then ask, okay, what do you see here? What is it? And again, give us feedback. Right now, we are in a setting where they don't directly use it, but they validate it as we go along. Or to support the histopathology and automatically have the classification of certain cell types and the amount of cells. And all this can be leveraged at the point of care due to our SHIP system that uses FHIR to unify heterogeneous data into homogeneous data, and our kite infrastructure, which hosts our own GPUs and our own storage systems, completely backed up and secure from the hospital by ourselves. And with this, I want to end the presentation. And I hope that I taught you that with synthetic data and virtual reality, we can do a lot more than just show cool stuff, but it does make life look better. And AI, especially in the hospital, requires that from multimodal data, you go to a standardized way of data where it's interoperable. And this is what FHIR does. It's an open source system framework that can be used anywhere. And then you need a modern IT infrastructure on your own premise, controlled by yourself to have full control of the data. Thank you very much.
Yeah, thank you very much for this fascinating insights. So please, for the audience, the chat is open and the Q&A tool for discussion. So maybe I would like to open up the discussion and ask you guys, you mentioned that this SHIP model was specifically developed for the hospital information system you're using at your premises. However, these data can be generalizable as well. How much effort would actually be involved to use such a model with other different hospital information system? And what's the level of AIs, or what's the level of general structure you need to be able to develop such a model?
So we have our SHIP group for this, as I show on the website. And if you look, there's an entire team. You would definitely need a separate team to maintain the system and to have this system good and well running. FHIR is completely open source and the documentation is out there, so I would say anybody can learn it. The main bottleneck is that the hospital has, as we saw, like 2 million data points, and they all need to be transformed into this FHIR format. And this is not doable to do manually. So for all different data types, in our case, we had 500, you need to set this up in a way that it's automated. And this is the biggest, let's say, bottleneck to actually implement this as another site. You need a team who per data source, let's say CT scan, MRI, observations, does this. Does that come close to answering?
Yeah, are there any sort of intraoperative data also involved? So I think what you showed us on the 3D instrument collection, that was independent from the other thing, but do you think these sort of different approaches could be merged as well?
Yes, definitely. So if you have video recordings, which you have a lot actually in the surgery with laparoscopic or minimal invasive surgery, these are data points within the system, and you can query them and you can get them, and even you can get them live. Now we're still in a synthetic phase, so we would definitely need to develop this for a non-synthetic phase, but it's doable because of the way it's structured.
Thank you. Maybe Luca, I have a question for you. In the current process of the editorial work, is there any routine check for the use of generative AI involved? And so maybe can you give us a bit of an idea of what's the current standard and where you think this will develop in the next 1 or 2 years, whether there is already an issue with researchers trying to integrate generative AI more than they should be, or whether this is not really a particular problem at the moment?
Well, when we receive a paper, from instance, from the European journal, we have some tool to check the plagiarism and the duplication of the manuscript. We have not, up to now, a clear AI detector. There are some detectors available online, but Clemens, it's more or less easy to find a paper mill by AI, because the structure is more or less similar. There is a repetition of the same concept in different part of the manuscript. The structure of the syntaxis of generative AI, it's more or less similar. So up to now, it's easy to find the scenario one. Or an authors with low skill and the use of a high quantity of AI to write a paper. It's really hard to find the scenario two. So a good writer that use sometimes AI to, for instance, write the limitation section. In this point, it's really difficult to distinguish between AI and human. I think that in the next 5 years, the AI inside the medical writing will grow, absolutely. But the growth should be done inside rules and inside a control, without the hyposchilia. The hyposchilia is the real key problem of a modern use of AI. I try, for instance, an AI for a reference manager. I cannot say the name because it's a brand, but it's amazing. You insert one citation, there is a logical map about citation. The AI suggests, okay, you could cite this, but for your discussion, it's better to cite this and insert inside the manuscript the correct way of reference. Really amazing, but it's a tool. I need my mind.
So at the moment, it remains on the editors to keep a close eye on undue use of generative AI. A question that was posed by Nuria Noah, whether it might not be possible to use these tools to facilitate the editorial process, like using analysis of the references or some other issues before sending out papers to reviewers, thus facilitating the review process per se. You think that might be an option?
It might be an option, but sometimes I found some reviewer that use generative AI to perform the review.
This is another issue. Yeah. So it's on all levels. So sorry, maybe a more general question for Anna, if you're with us, or maybe
Yes,
also
I am still.
Luca and Gijs. So what do you think is the area where machine learning or artificial intelligence will have the most impact on thoracic surgery? Will it be intraoperative technical issues like in robotic surgery, or like the 3D annotation and all further developments that might come out of it? Or do you think it will be more in decision-making processes or sort of patient selection based on risk variables? What do you think are the major fields where AI will have an impact?
Well, I think basically, and I'm sorry, I don't know if you can hear me now correctly because I'm in the airplane right now. I think the most important part, and that where most of the new technology of the AI is implemented right now, is in the diagnostic part, in the image diagnosis. And the next one, I think it will be the simulation and the training. And then probably lastly, it will be the surgery application, real-time surgical applications. I think that would be more natural development of the technologies. I'm not sure if this answers your question. But I hope so.
Yeah, thank you. That seems like very realistic estimation. Luca, you have any ideas on this?
No, but I agree with Anna about this.
Guys, anything to add?
I see in our clinics the same what Anna mentioned. It's mostly about the image data, and then it's about assisting. And I think it will assist a lot in combining data sources. So we cannot look through all the documentations of years of history, but with the chat models and the rec systems out there, we can basically ask the AI, okay, what did you find? And bring me to these data points. And now I can read the relevant documentations quickly. I think automation and helping the doctor is the biggest step. And surgery is definitely one of the latest steps where we first have to see before we believe.
Yeah. Any questions from the audience or in the chat? If this is not the case, then I would really like to thank all the three of you for the excellent presentations and the interesting discussions today. I would also like to invite you to join us for our next upcoming ESDS webinar, which will take place on April 7th and will be on the management, will be an Oxford-style debate on the management of thoracic trauma with Didier Ladinois and Eric Delos, and looking forward to welcoming you there. Thanks for joining in today, and have a nice evening.
Thank you.
Thank you. Bye.
Bye-bye.